lecture we are going to continue our discussions on kinematics of rotation. We were discussing parametrization of the rotation matrix and visualization of rotation. Here we will also look at the representation of angular velocity vector, and we are going to represent the angular velocity vector in terms of the parameters, the rotation parameter rates. Now, parametrization of rotation, this discussion we had started in the previous lecture. Why do we need to parametrize rotation? Because we need to represent this rotation matrix in terms of the minimum number of variables, and as you know, rotation can be represented by 3 parameters. So, we would like to know how the rotation matrix can be written in terms of these 3 parameters. And these 3 parameters are just like when you represent the position of a particle, you have x, y, z with respect to certain origin, with respect to certain coordinate system. Similarly, when we represent a rotation matrix, it represents an orientation of the body. It represents an orientation of the body in terms of these 3 parameters. Just like position is represented by x, y, z in a certain coordinate system, similarly rotation or orientation of a body is represented by these 3 rotation parameters, but not all parametrization of rotation matrix has 3 parameters, some have more, and we are going to look at one of these. Euler parameters, they are also known as unit quaternions. As the name suggests, quaternion, there must be 4 parameters. This uses the axis angle representation. Given given a unit vector n cap and a rotation about that vector, we have seen how to represent a rotation matrix. Therefore, given this n cap and theta, these are actually 4 parameters, the nx, ny, nz components of the n vector, of course satisfying the constraint nx square plus ny square plus nz square equal to 1, and theta. So, we have nx, ny, nz and theta 4 parameters, but there is a constraint. So, ultimately we have 3 degrees of freedom as expected. Let us define something called lowercase e naught, E0 as cosine of this theta by 2. Theta is the rotation about that axis n cap. So, given an orientation or a rotation matrix corresponding to n cap and theta, let us define E0 as cosine of theta by 2, and another vector E consisting of E1, E2, E3 as components equal to sine of theta by 2 times nx, ny, nz, the n cap vector. Therefore, this E vector is nothing but sine theta by 2 n cap vector. So, this is nothing but sine of theta by 2 n cap vector. Now, there are 3 there are this E0 and E vector. So, 4 parameters. Of course, there is a constraint as I have written here, nx square plus ny square plus nz square is 1. So, it has 3 degrees of freedom. Nevertheless, we have 4 parameters, and to visualize this I cannot draw a 4 dimensional space. Therefore, what I have done is I have represented the vector E as this plane, horizontal plane, and E naught as orthogonal to this plane. Even though I am drawing it like a plane, this is a 3 dimensional space, and this adds to it, E naught direction adds 1 more direction, therefore, it is a 4 dimensional space. Now, this you have to stretch your imagination a little bit and think about representing a point in this space, in this 4 dimensional space. we have a vector E and certain value of E naught, and therefore, this point represents an orientation of the body. This point represents an orientation of the body. It represents a rotation matrix, and every rotation matrix, remember, represents orientation of a body. These 4 parameters E0, E1, E2, E3 are known as the Euler parameters, and with this constraint that E0 square plus E1 square plus E2 square plus E3 square is 1, which you can very easily check. Therefore, finally, even though we have 4 parameters, we ultimately have independent only 3 parameters which are independent. But this 4 parameter representation is very useful because it avoids singularity in representation. Now, this is an equation of a sphere in a higher dimensional space. In a 4 dimensional space, this is a sphere, just like in 3 dimensional space, x square plus y square plus z square is r square is a sphere. So, we say that this is a 2 sphere in 3 dimensional space, a 2 sphere, that means the surface of the sphere is 2 dimensional. So, it is a 2 sphere in 3 dimensional space. This is a 3 sphere represented as S3, s to the power 3, 3 sphere in 4 dimensional space. Now, that is an interesting visualization of the Euler parameters, that rotation is decided by a point on a 3 dimensional sphere embedded in a 4 dimensional space. You can always visualize these things by considering a lower dimensional sphere. Now, these Euler parameters, it uses the axis angle representation. These are the finally our parameters and the constraint, and we have found that these 4 parameters always lie on a unit sphere, unit 3 dimensional sphere in 4 dimensional space. What is 0 rotation? No rotation. So, it is at the origin, just like a particle when it is at 0 0 0, it is at the origin. Then what is the representation on this sphere? Because the point of the identity matrix, identity rotation matrix, that must be represented, that must have a representation in these 4 parameters. When theta equal to 0, then this E, the Euler parameters become 1 0 0 0, because theta is 0. So, cosine theta by 2 is 1 and the rest of the things are 0, because sine theta by 2 is 0. Okay. So, this is this 0 identity rotation matrix, or in the base orientation, the point is at the north pole. The point is at the north pole. It is E0 is 1 and other components are all 0, therefore, it is the north pole. When it represents 360 degree rotation, a complete rotation of 360 degree, then what happens? If you just put theta as 2 pi radian, when you put theta as 2 pi radian, you will get minus 1 0 0 0. In other words, 360 degree rotation is the south pole, minus 1 0 0 0 is the south pole of the sphere in 4 dimensional space. So, we are visualizing, we are drawing analogy with the 2 sphere, though remember that this is a 3 sphere. So, therefore, it is an antipodal point, it is just a point lying opposite to it, diametrically opposite. Therefore, 360 degree rotation is represented at the south pole and 180 degree rotation is on the equator. Now, because 0° rotation and 360° rotation, they are same orientation, absolutely same orientation. Therefore, these 2 points are identified. This point and this point represents the same orientation, and similarly plus 180° rotation and minus 180° rotation, again diametrically opposite points, antipodal points, they are also identified. Therefore, diametrically opposite points are what are known as antipodal points, represent the same orientation. Now, any point on the sphere represents a rotation or orientation, because orientation is represented by this rotation matrix. If the rotation matrix is identity, then there is then we are at the kind of origin of the orientation space. We are at the origin of the orientation space, just like 0 0 0 position is the origin of the position vector. And then if you want to locate a point or a particle, let us say a particle is at 1 2 3, then you move 1 unit in the x axis direction, 2 units in y axis direction, 3 units in z axis direction, and you locate the particle. Similarly, there must be an origin of the orientation space, and the origin is where the rotation matrix is identity matrix, and any point on the sphere represents a rotation of the body or an orientation of the body. Orientation is therefore represented by rotation, a rotation matrix, and rotation matrices are parametrized by certain parameters like Euler parameters, Euler angles we have seen. We are now looking at Euler parameters, and we have also looked at axis angle parametrization. Changing orientation would mean that there is a motion of this point on the sphere. As the orientation changes, the point on the sphere must be moving, and therefore, between two orientations or two rotation matrices, there you can think of a path joining these two orientations. For example, from the identity matrix to let us say this orientation, there can be multiple paths. And these paths, remember, are all on this unit sphere. It is a 3 sphere in 4 dimensional space. And now you can think of how you can visualize, first of all, how orientation is changing, just like you visualize change of position of a particle, which is indicated by change in the coordinates. Similarly, change in these parameters will indicate change in orientation. We have already looked at this yaw pitch roll parametrization. Now, we are going to use these parameters to find out or to represent these parameters and their rates to represent angular velocity. Remember, I had mentioned this in a previous lecture, that angular velocity vector is not an integral of, the angular velocity vector is not a derivative of any other vector. Angular velocity vector is not a derivative of any vector quantity. Therefore, we cannot integrate the angular velocity vector just like that, because it is not a time derivative of any other vector quantity. Therefore, we cannot integrate it straightforwardly. Therefore, what we are going to do is, we are going to represent angular velocity vector in terms of the yaw pitch roll parameter rates, these parameters and their rates. We are going to represent angular velocity vector as a function of these yaw pitch roll parameters and their rates. Now, this is because why this is required, as I mentioned, angular velocity is not the time derivative of any vector quantity. Remember or recall this axisymmetric body moving, spinning and precessing and nutating, the general motion of an axisymmetric body that we have discussed. We had represent this angular velocity vector, you recall that we had represented this angular velocity vector in this form: nutation I cap, component of precession j cap, and this is the combination of component of precession and the spin in k cap. Here we have represented the angular velocity vector in terms of these parameters and their rates, psi theta phi and psi dot theta dot phi dot. Of course, only theta is present here, psi and the spin rates were not present, because we have assumed that the spin was constant and it does not contribute, that angle does not contribute because the body is axisymmetric. Therefore, we had earlier already represented angular velocity vector in terms of rates of these parameters theta, psi and phi dot was constant equal to p. So, it is written here, phi dot is p. So, the orientation parameters were psi theta phi and their rates were psi dot theta dot phi dot, and we had represented angular velocity in terms of these rates. Now, that is what we are going to do for in general angular velocity vector using the yaw, roll and pitch coordinates or their angles and their rates. We are going to represent the angular velocity vector in terms of the rates of yaw, pitch and roll coordinates. We will look at a body fixed frame. We have discussed this before. We will use a body fixed frame to represent these parameters and their rates. Now, this part we had discussed in a previous lecture. You have to recall that the rotation matrix, which actually represents an orientation of the body, in terms of the yaw, pitch and roll coordinates was represented or obtained like this, that we first rotate about the z naught axis by an angle psi, which is the yawing angle, this yaw angle, then about y1 new y axis, about y1 by an angle theta, and then the new x axis, which is x2 by an angle phi, which is the roll. And since all rotational transformations are taking place with respect to the new axis that is obtained every time, therefore, this sequence is post multiplied to obtain the net rotation matrix from frame 3 to frame 1. And this rotation matrix, remember, represents an orientation corresponding to these coordinates psi, theta, phi, which means if I give you psi, theta, phi, you should be able to tell me how is the orientation. You should be able to tell me what is the rotation matrix, and every rotation matrix represents an orientation. Therefore, we will know the orientation corresponding to the coordinates psi, theta, phi. These were the fundamental rotation matrices about z0, about y1, about x2 by angles psi, theta, phi respectively, and we had multiplied these 3 rotation matrices in that sequence which I have written and obtained this expression of the rotation matrix. This is quite a complex expression, and I will leave it to you to check this by multiplying these 3 matrices. Now, how do we represent the angular velocity vector of this body in its body fixed frame? Using the rates of yaw, pitch and roll. How do we represent the angular velocity vector in the body fixed frame using the rates of yaw, rate of yaw, rate of pitch and rate of roll, that means psi dot, theta dot and phi dot. How do I represent the angular velocity vector? So, to do that, you see psi dot is the rate of change of the yaw angle, and that is taking place about the z naught axis, because whole psi has been defined as a rotation about the z naught axis. Therefore, psi dot must also be represented about that z naught axis, but z naught axis, because now we want to represent the angular velocity in terms of the body fixed frame, which is x 3 y 3 z 3, we must represent z naught in the frame x 3 y 3 z 3, and that is what I have written. Therefore, psi dot is about z naught cap, but represented in x 3 y 3 z 3. Similarly, theta dot, which is the pitching rate, which is about y 1, but now represented in x 3 y 3 z 3. Similarly, the roll rate, which is about x 2, roll rate is phi dot, which is about x 2, but we have to now represent that x 2 cap vector in x 3 y 3 z 3. Then we have, by adding these, superposing these three, or vectorially adding these three individual component vectors, we will get the angular velocity in the body fixed frame x 3 y 3 z 3. So, this is our angular velocity vector in the body fixed frame x 3 y 3 z 3, represented as a vector sum of yaw angular velocity vector, which is about z naught, but now represented in the x 3 y 3 z 3 frame, pitching angular velocity vector, which is about y 1, but represented in x 3 y 3 z 3, and similarly added to that the roll rate angular velocity vector, which is about x 2, but now represented in x 3 y 3 z 3. Let us look at these fundamental rotation matrices and our final rotation matrix. I have written out the rotation matrix about z naught by an angle psi. The second column of this represents y 1 in frame 0. This is our interpretation, because r z 0, this is the first rotational transformation, r z 0 by an angle psi. The yaw was the first rotational transformation. Therefore, the second column must represent y 1 in x 0 y 0 z 0. The second column represents y 1 in x 0 y 0 z 0. Third column represents z 1 in x 0 y 0 z 0, and because it was a rotation about z 0 itself, therefore, z 0 and z 1 are actually identified, that is why it is 0 0 1. 0 0 1 is z 0 represented in z 0 or z 1 represented in x 0 y 0 z 0. Both are same, because psi was about the z 0 axis. What do we need? We need this z 0 in frame 3, representation of z 0 in frame 3, and representation of y 1 in frame 3. We need representation of z 0 in frame 3, representation of y 1 in frame 3. Now, representation of z 0 in frame 3 can be easily obtained by using this transformation, but in the inverse fashion, because this takes a vector in third frame to 0th frame. If I write this, which is nothing but r 3 0 transpose, is an inverse. So, it must take a vector from the 0th frame to the third frame. Therefore, z 0 in the third frame must be r from 0 to 3, z 0 in the 0th frame. And if I do that, z 0 in the 0th frame is nothing but 0 0 1. What does it do? It filters out the third column of this matrix, and third column of this matrix is nothing but the third row of this matrix, because the transpose of this matrix is this matrix. Therefore, it filters out the third row of R from 3 to 0, or the third column of R from 0 to 3, third column of R from 0 to 3, the rotation matrix from 0 to 3. This is the third column. So, this is Z 0 represented in x 0 x 3 y 3 z 3. This is Z 0 represented in x 3 y 3 z 3. In a similar manner, we are going to determine y 1 represented in x 3 y 3 z 3. Y 1 in the 0th frame is this, and therefore, if I use the rotation matrix from 0 to 3, if I use the rotation matrix from 0 to 3 and transform y 1 in 0, then I will get y 1 in 3, representation of y 1 in 3, and that is what I have done. In other words, I have taken this is nothing but transpose of this, and I have multiplied by minus sin psi cosine psi 0. And what do I get? I get 0 cosine phi minus sin phi, that is y 1 represented in x 3 y 3 z 3. And x 2 represented in x 3 y 3 z 3 is same as x 3 in 3, because the last rotation, which was a roll angle rotation, there it was a rotation about x 2, and therefore, x 2 and x 3 are identified, and hence x 2 represented in x 3 y 3 z 3 is same as x 3 represented in x 3 y 3 z 3, which is 1 0 0. Now, our task is straightforward. We have to just substitute these expressions in the angular velocity expression, which is written as the first equation here, and what I have done is now substituted them and pulled out the yaw, pitch, roll rates as a column. This gives us the transformation from the yaw, pitch, roll rates to the angular velocity vector, and this is a very useful transformation. Using this, now we can integrate, we can integrate omega, at least numerically we can definitely do integrate and find out the evolution of psi, evolution of theta, and evolution of phi. We will finally write down the rotational dynamics equations in terms of psi, theta, phi and their time derivatives. And from here I can also find out angular acceleration by time derivating this. I can also find out angular acceleration. Therefore, this is a very useful transformation from the yaw, pitch, roll rates to the angular velocity vector. We can have a general approach. Suppose we have the rotational transformation rotation matrix R from 3 to 0 in terms of psi, theta and phi. I take the time derivative of this matrix, that means time derivative of individual components of this matrix, and it will be a rotation matrix which will involve psi, theta, phi, psi dot, theta dot, phi dot, and psi, theta, phi need not necessarily be yaw, pitch, roll, it can be any other Euler angle parameters, for example. Now, note this we have discussed under kinematics, that d dt of a vector is omega cross the vector, because this is a unit vector, these are the frame vectors. d dt of the frame vector is omega cross the frame vector. Similarly, dy dt is omega cross y, dz dt is omega cross z, and therefore, r from 3 to 0 dot is nothing but dot of these columns. It is nothing but the dot of these columns as I have written here, derivatives of these columns, and derivatives of these columns are individually omega cross those columns. Therefore, omega cross can be pulled out, and we can write omega cross in terms of the Rodrigues form. I have written it like this capital omega. We have discussed Rodrigues form is a skew symmetric form of this vector, and write the time derivative of r from 3 to 0 times is equal to the Rodrigues form of omega times r from 3 to 0, and then I can find out omega, the Rodrigues form of the angular velocity vector, as the time derivative of the rotation matrix 3 to 0 multiplied by the transpose of rotation matrix from 3 to 0. Why? Because I have inverted this. I have written this as in this form, and remember, this is very important to note the order. If it is post multiplied, it must be post multiplied when it is inverted, and this implies omega is equal to r from 3 to 0 dot times inverse of a rotation matrix is nothing but its transpose. And from here now Rodrigues form I can read out the individual components of the angular velocity, and this is a very general approach. This is a very general approach. You can do this for Euler angle representing angular velocity in terms of the Euler angles, for example. So, to summarize, we have looked at parametrization of the rotation matrix in terms of the Euler parameters. We have looked at visualization of the rotation matrix and how a rotation matrix represents an orientation of the body, and finally, we have looked at a very important representation of the angular velocity vector in terms of the yaw pitch roll rates, and also discussed a very general approach to find out angular velocity vector in terms of any orientation rates. It can be Euler angles, it can be yaw pitch roll, any other orientational angle rates. So, with that I will close this lecture.